Hey y'all, sorry about that. Seems like I got interrupted partway through by a technical error. Luckily, I checked. First half of the video is still intact, so let's try to pick up where we left off. I think I said something about doing another example, and let's see here. Let's determine where f of x equal to x squared plus 2 to the 7/2 power is concave up or down. And let's find any inflection points, since we'll kind of get those along the way. Okay, well, to find inflection points, we should get to that second derivative. First derivative, let's use the chain rule. If we let u equal x squared plus 2 and y equal f of x, which would be u to the 7/2 power, we get that f prime of x is dy dx, which by the chain rule is dy du times du dx. dy du by the power rule is equal to 7/2 u to the 5/2. And du dx is just going to be, by the power rule and the sum rule, 2x. And if we put that up here, that will be equal to 7/2 times 2, cancels out. We're left with 7x times, back substituting for u, x squared plus 2 to the 5/2 power. Nifty. Now we need to find the second derivative. F double prime of x is derivative with respect to x of 7x times x squared plus 2 to the 5/2 power. By the product rule, that's equal to 7x times derivative with respect to x of x squared plus 2 to the 5/2 plus x squared plus 2 to the 5/2 times derivative with respect to x of 7x. Alright, computing those derivatives, you can do this one the exact same way as you did this one over here using the chain rule. Good exercise for you to check would be that this would be 7x times 5/2 x squared plus 2 times 2x plus x squared plus 2 to the 5/2 power. Sorry, x squared plus 2 to the 3/2 up there. X squared plus 2 to the 5/2 times 7. So, good step check. Make sure you can get from this step to this step. Doing a little bit of prettification. Yes, I invented that word just now. That'll give you 14x squared, 35. How about that? 35x squared times x squared plus 2 to the 3/2 power plus 7 x squared plus 2 to the 5/2 power. Alright, and now we need to solve when this thing is equal to 0. Let's do it. So let's remember, our original function was x squared plus 2 to the 7/2. Okay, this is our second derivative. We need to solve when that is equal to 0. Let's note, it's never undefined, since even though we have square roots flying around, x squared plus 2 is always positive. So nothing ever goes wrong. Solve when it's equal to 0. We need to solve 35 x squared times x squared plus 2 to the 3/2 power plus 7 times x squared plus 2 to the 5/2 power equals 0. All right, let's factor some stuff out and see what we get. You could also subtract and divide and work with it that way. I personally prefer the factoring approach, so them's the bricks. I'm here. If you factor, you can factor away a 7 x squared plus 2 to the 3/2 power from both things. You'll end up with 35 x squared here plus x squared plus 2 from here equals 0. How do you get those things? Okay, well, factoring that out from here, oh, this shouldn't be 35, it should be 5. That first factorization should be fairly obvious. This one here, okay, the 7, good. If we factor out x squared plus 2 to the 3/2, we're left with x squared plus 2 to the 5/2 minus 3/2, which is 2 over 2, aka just 1. So plain x squared plus 2. So in other words, we need to solve 7 times x squared plus 2 to the 3/2 times 6x squared plus 2 is equal to 0. All right, this is going to be 0 whenever any of its factors are 0. So now we solve x squared plus 2 to the 3/2 equals 0. And this will happen when multiplying both sides, so you get take the 2/3 power on both sides, you get x squared plus 2 equals 0, which means that x squared equals negative 2. So, no, can't happen. And then we further solve 6x squared plus 2. Equals 0. And that'll also never happen, right? Do some work, that gets you x squared is negative 1/3. Can't happen. So, f double prime of x is never 0, which means f has no inflection points. We can just conclude that straight off the bat. We still want to find when f is concave up or down though. Well, if we have no inflection points to check, no critical numbers to check, the whole number line is just a single interval. And we can pick a test point anywhere. I'm going to choose 0. Let's note that f double prime of 0 will equal, let's see here. Plugging in to our function, we get 0 plus 7 times 2 to the 5/2. That's going to be strictly greater than 0. So, f is concave up on R. Everywhere. Our function is going to be concave upwards. That's cool. It means the function looks something like that. Alright, that's it for that example. Let's move forwards. As I proceed to sort through my notes, since they got all out of order during the tech era. talked about that, talked about that, talked about that, talked about that. Ah, here we go. All right, so you might say, well, if all the second derivative can do is talk about concavity, great, I don't care. But the second derivative can actually be even more useful. So let's look at this picture. Let's say we have 2 points A and B, and the graph of our function looks something like this. So this is our function f. We notice, hey, it looks like A is relative max and B is a relative min. Which is great. We know how to find those using the first derivative test. But the first derivative test required a lot of checking, right? We had to pick our test points, checking on both sides, and then we had to be like, okay, does it change sign like this, going from positive to negative, or does the first derivative go from negative to positive? A lot of things to keep track of. But if the function is twice differentiable, we can actually make this process easier, right? Let's notice f prime of A equals 0, and f prime of B is equal to 0, but f double prime of A is less than 0. And here, f double prime of B is greater than 0, because the function is concave down there and concave up there. This gives us a hint to a new derivative test that will allow us to find minima and maxima of functions. We call it the second derivative test. Get a new piece of chalk. Alright, so what does the second derivative test say? Second derivative test says, hey, if your function f is twice differentiable, we can compute minima and maxima more easily. To compute relative extrema, step 1, compute f prime of x and f double prime of x. Thankfully, you get this one all the way to that one. Step 2, find critical numbers of f. Where f prime of x equals 0. We don't need to worry about any of the undefined critical numbers, right? Because we've said that the function is twice differentiable. Step 3, compute f double prime of c at each critical number. C. Alright, and so what are the results? Let's continue that over here. So we've already found that these are points where the first derivative is 0. Then, if the second derivative is less than 0, f has a relative max. Heck, I'm going to erase the picture up top. So get that down if you haven't. So I think I'm saying if f double prime of c is less than 0, f has a relative max at x equals c. Same thing is true the other way. If f double prime of c is greater than 0, then the function will have a relative minimum. At x equals c. So both of those results make sense. It's a point where the tangent line to the function is flat. First case scenario, you're saying, oh, something like this is happening, right? It's flat there and curving downwards. Clearly, that's going to be max. It's going to be the top of a hill. And the other one is the situation to describe the bottom of a valley, which are perfectly our conditions for local minimums and maximums. But you get a third thing as well. Well, you don't get a third thing, but there's a third case that can happen, right? If the second derivative is neither negative or positive and it's just 0, or doesn't exist, the test is inconclusive. You don't know either way. It could be either. So, what do? You resort to the first derivative test. So that's all there is to it. A very quick example where you might fall into case C, f of x equals x cubed, right? That would be one where you had that inflection point at x cubed, aka a point where the second derivative was 0, first derivative was also 0 there, and it would end up being neither a minimum or a maximum. So it could be a min, max, or neither. Test is inconclusive. Hit it with the first derivative test. All right, let's do a couple examples, and then I think we'll call it good. Let's find the relative extrema of f of x equal to 3x cubed minus 2x squared plus 32x minus 4. Alright, step 1, let's compute the first and second derivatives. F prime of x will be 3 times 3, 9x squared minus 2 times 2, 4x plus 32. And f double prime of x will equal 18x minus 4. Okay, now we need to compute the critical numbers of f where f prime is 0. So to do that, let's set. So that's step 1. Step 2, we solve f prime of x equals 0. By the quadratic formula, x is going to equal, right, we have a quadratic here. I'm just going to use the quadratic formula for it. I don't feel like factoring. It'll be 4 plus or minus the square root of negative 4 squared, okay, 16, right? So we have negative 4 plus or minus square root of 16 minus 4 times 9 times 32 divided by 18, which, let's do some quick maths off screen. Alright, after that off-screen math, just arithmetic to simplify. You can see the remnants of my work there. Should be 4 times 9 is 32. You'd end up with 2 plus or minus 2 times the square root of negative 71 over 9. And these are not real numbers, right? They're complex numbers, which means if we were doing complex calculus, which you can do, those would be valid, but they aren't here. So, those are not real numbers. Therefore, f prime of x has no zeros. F of x has no critical points. F has no critical points. Hence, no relative extrema. Kind of an unsatisfying answer, but them's the bricks. Let's do another one. Let's find the relative extrema and any inflection points of g of x equal to 1/12 x to the 4th minus 1/2 x squared. Alright, well, let's begin with the second derivative test. Computing the first and second derivatives. Oh, yeah. Alright. So g prime of x, by the sum rule, power rule, and constant scalar multiple rule, we get 4 times 1/12, 4/12, which is 1/3 x cubed, minus 2 times 1/2 is 1, so minus x. Alright, and then g double prime of x would give us 3 times 1/3 is 1, so we'll have x squared minus 1. Alright, let's find critical points. So we solve g prime of x equals 0, aka 1/3 x cubed minus x equals 0, factoring the polynomial. That tells us 1/3 x squared minus 1 all times x is equal to 0. So either x equals 0 or 1/3 x squared minus 1 equals 0. And in this case, 1/3 x squared equals 1, x squared equals 3, so x is equal to plus or minus square root of 3. Alright, so those are our 3 candidates to check. Now, what we're going to do is we're going to plug them into the second derivative and see what they spit out. Alright, so let's save those up here. Once you've solved g prime of x equals 0, you get that x equals 0 or x equals plus or minus square root of 3. Second derivative test says all you have to do is check them here. You don't need to make a split number line. G double prime of 0 is equal to 0 squared minus 1, negative 1, which is less than 0. G double prime of positive square root of 3 is, square root of 3 squared is 3. 3 minus 1 is 2, which is strictly greater than 0. And G double prime of negative square root of 3 is also going to be 2, which is greater than 0. So the second derivative test has a conclusion for all of these. What the second derivative test says I guess I shouldn't have erased those. G prime of x equals 1/3 x cubed plus x. G double prime of x plus x squared minus 1. Alright. So, by the second derivative test, we can now finish this first portion, finding the relative extrema. G double prime of 0 is negative 1, which is less than 0. So, G has a relative max at x equals 0. And both of these were greater than 0. Therefore, G is going to have relative mins at plus and minus square root of 3. Sorry, my voice is getting a little bit hoarse. I lectured on for quite a bit after the tech error without realizing that things were going wrong. So, kind of shot my own voice out. Alright, relative maximum at x equals 0, relative minimum at x equals plus or minus square root of 3 by the second derivative test, which again just says, hey, find the first derivative, find the zeros of the first derivative, plug them into the second derivative, and check their sign. But now we also wanted to find any inflection points. Right? So we resort to our procedure for finding inflection points, which are points where G double our test points are points where G double prime is 0 or does not exist. So, as we go about finding our inflection points, we solve 0 equals G double prime of x, which is x squared minus 1. Okay, x minus 1 times x plus 1. So that tells you x is plus or minus 1. So those are our two candidates for inflection points. Now, how do we check those? We examine the sign of f double prime of x, or g double prime of x in this case, on both sides. So negative 1, 1. Let's choose those as our test points. Negative 2, 0, and 2. And we're again checking the sign of g double prime. Alright? So, if you plug negative 2 into g double prime of x, you get 4 minus 1, which would be 3, aka a positive number. If you plugged in 0, you get 0 minus 1, negative. Plugged in 2, you get 3, which is positive. So we see that g double prime changes sign at both negative 1 and 1. So G has inflection points at negative 1, comma, and then plugging negative 1 into the original function, you get 1/12 minus 1/2, which is negative 5/12. twelfths, and at 1, negative 5 twelfths. Again, plugging 1 into your original function, right? Since inflection points are defined as being the full point. Alright, that's a few applications of the second derivative, and in the next couple videos, we'll start talking about, hey, well, what's all this good for? We can talk about relative mins and maxes of functions. Let's get some real-world examples in there. So next video, we'll be building up to those real-world examples, kind of polishing off our techniques, and then the video after that, section 4.5, will be just all real-world examples and such. All right, see you guys there.